What's up, scholars? Today we're going to be finding zeros of polynomials using synthetic division. You know how to find zeros of polynomials when the highest power is x squared here. But we use synthetic division when we have polynomials like x cubed, x to the fourth, and so on. I think I said in class I don't really care for synthetic division, but I must say it is extremely useful and it is much easier than regular division of polynomials. So let's get started. The way that you start to find numbers that you're going to test to divide synthetically is kind of like how you would do a normal quadratic, where you would take the first term and the last term, the coefficients there, or the constant and the leading coefficient, and you would multiply those two together, right? We're going to do the same thing here. In this case, it's really easy. Leading coefficient is 1, and my constant is 2, and so 1 times 2 is 2, and so I'm just going to list all the factors of 2. And so the only factors of 2 are 1 and 2 because it's prime. But that just basically means that I could get my zeros for this polynomial function could be at plus or minus 1 or plus or minus 2. And this is all divided by 1 anyway, because my leading coefficient's 1. So I'm just going to start testing these numbers and trying using synthetic division to figure out if I have any zeros at 1 or 2. So let's do that. So first, I'm going to try the number +1. I like to start with the smaller numbers first. And so +1, I'm going to divide into, and then you just take basically all of the coefficients and you write them out. So I'm going to have a 1, a 4, a 5, and a 2. Okay. You bring down this leading number right there, and then you begin. 1 times 1 is 1. 4 and 1 make 5. And I made a mistake. So here we go. I'm going to drop the 1 down. And then 1 times 1 is just 1. 4 plus 1 is 5. 1 times 5 is 5. 5 plus 5 is 10. 1 times 10 is 10. And then 2 plus 10 is 12, which is not 0. What I'm trying to get is I'm trying to get a remainder of 0. So I got 12 here. So that is no go. It's no bueno. So 1 is +1 is not a factor. Then you just continue to go down the line. This is why I don't like synthetic division, is it feels like voodoo, and you can possibly have a bunch of factors to try. But we'll try -1. Because again, starting with the lower numbers is always easiest. So I'm going to write down my leading coefficients again, 1, 4, 5, and 2. I'm going to drop down this 1, and -1 times 1 is -1. 4 plus -1, or 4 minus 1 is 3. -1 times 3 is -3. 5 and -3 make 2. -1 times 2 is -2. Oh, thank goodness. All right, boom. 2 minus 2 is 0. We get a big fat 0. We are super happy. Yes. That means that one of our zeros is x equals -1. So then I can, the cool thing about this, and again, here's the voodoo part, but the cool thing about this is that now that I have this, I can write this as a factor. Remember to swap this sign for the zero product principle. So now I'm going to have x plus 1. And then my other factors, what I'm factoring this polynomial into, they're right here, which is super cool. And they're in hierarchy. This is going to be x squared. This is going to be x to the 1. And this is going to be x to the 0. So I'm just going to take these numbers and put them as my coefficients on here. So I'm going to say I'm going to have 1x squared plus 3x plus 2. And boom, this thing, now I have this down to a quadratic. I know how to factor x squared plus 3x plus 2. Like, I'm good. 1 times 2 is 2. Factors of 2 that add to 3 are 1 times 2. Fabulous. So easy. So I'm going to have x plus 1, x plus 2. And then that's still there. Oh, look. This has a multiplicity of 2. And so now my factors, or my real zeros, are going to be x equals -1 and x equals -2. Whew, okay. So like this one wasn't that bad, right? Those are my zeros. And so this polynomial is crossing over the x-axis on the graph here and here. So this wasn't that bad, but we're going to get higher degree polynomials, and these numbers can get quite large, and then you're testing a lot of them. So let's just look at one of those. Okay, here we go. This is a 4th degree polynomial, so it's a little bit more hardcore. There's a lot more terms here. I can't just factor this by grouping. It's not easy, so like we really need synthetic division. So again, first always start out with listing all the possible rational zeros. What are all the possible rational zeros? Well, it's 1 times -32. It's all the possible factors of 32, or plus or minus all the possible factors of 32. So I love doing these little trees. So I'm just going to figure out what that is. And then 4 is like 2 times 2. Okay, so all my possible factors of 32 are, oh, don't forget 1 and 32, right? No prime factorizations, but those are all the possible factors for this polynomial. So I could have plus or minus 32, plus or minus 16, plus or minus 8, plus or minus 4, plus or minus -2, or plus or minus 1. That's a lot of factors to test, right? And of course, it's all divided by 1. This is a lot of factors to test. But, I mean, it's only, there's 6 there, and the positive version, the negative version. It's only 12. It's fine. It's fine. So this guy right here, again, I really like to start with the smaller numbers. I don't know if 1 is gonna, I don't know if 1's gonna work or not, plus or minus 1. I think I'm just gonna start with 2 this time. There's no rhyme or reason to it. So do our synthetic division to check all of these zeros. Ugh, crazy. All right, so I'm gonna write down my leading coefficients, right? I'm gonna have 1, -1, 14, -16, and -32. All right, and then we just jump right in. So I'm going to bring down this first term, or first number, I guess. 2 times 1 is 2. 2 and minus 1 make just 1. 2 times 1 is 2 again. 14 plus 2 is 16. 2 times 16 is 32. 32 and -16 is 16. Ooh, 2 times 16 is going to be 32 again. Yes, yes. Okay, so now -32 and +32 add to 0. Oh, I'm so happy about this. Like, I was really nervous this was going to take me like 3 pages. So that means that x equals 2 is where this polynomial crosses the function. Like that's one of my zeros. So, wow, that like, I'm so excited. Okay, so again, like all of these numbers. So now I'm going to write this out. So x equals 2. So x minus 2 is one of my factors. And then these are all written in hierarchy. They're going to be, this one's like in my x cubed, this one's x squared, this one's x to the 1, and this one's x to the 0. So then my other factor for this polynomial is 1x cubed plus 1x squared plus 16x plus 16. Oh my gosh, that's fantastic. Oh, and you know what else? Okay, so you have choices here. You can either, because this is an x cubed, you can either perform synthetic division again on this guy and list out all the possible factors of 16 and like start testing them and blah, blah, blah. I just happen to notice that we can factor this by grouping. Like, so exciting. So exciting. Look at this. Both of these terms have a 16, and then both of these terms have at least an x squared. I haven't done it in my head yet, so I'm not sure if it's going to work out, but I'm going to give it a shot. So do you remember before when you were factoring regular quadratics, like when you were factoring regular quadratics, something like x squared. I don't know if I've talked to you about factoring by grouping or not, or if I've mentioned that. So I'm just gonna like side note over here. You wanna find two numbers that multiply to 6 but add to 5. And so multiply to 6 but add to 5, those are gonna be 3 and 2. And you're, since this is like a level 1 factoring problem, the leading coefficient's 1, you can just automatically write down your factors as 3 and 2. But another way to look at it is like to split this middle term, and then you have like x squared plus 3x plus 2x plus 6. And really 3x and 2x was still just 5. And then you just like factor one side, and then you factor the other side, see what you can pull out. That's what we're doing here. I just happen to notice that this is 16 and this is 16. So this is going to make my life actually a lot easier. So let's give this a shot. Okay, both of these have at least an x squared that I can pull out. And then I'm left with x1, and then both of these have a 16 that I can pull out. And I'm left with, oh, yes, 16 times x gets me back to 16x. 16 times 1 gets me back to just 16. Oh my gosh, as long as these two match, as long as they're the same, then it's basically like I'm factoring both of these out. They become their own factor. And then whatever you're left over with is its own factor. Oh my gosh, that's fantastic. And then this guy is still, he comes down for the ride. And boom, this whole thing up here equals this in the factored form. So now I know what my zeros are. Super, super awesome. I have a 0 at x equals 2. I have a 0 at x equals -1. And I even have, look at this, I'm noticing I'm going to get an imaginary 0 popped out for us. So this one, if I set it equal to 0 using the zero product principle, and then I solve for x, I'm going to minus 16 from both sides. And then in order to undo that square, I need to take the square root. And then boom, x equals, now square root of a negative is always going to be the I. And the square root of 16 is 4. X equals 4i. So there's some imaginary numbers. Oh, and I almost forgot, plus or minus 4i, plus or minus 4i. So there's our there's our zeros. And when you hit in this case, because it was like x to the fourth, I was able to factor by grouping. But like we saw in the previous example, as soon as you get it down to like x squared, blah, 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 like in this form, like a standard form of a quadratic, then you can use like how you know how to factor in order to get that quadratic down. All right, have fun.